Hello everyone, my name is Jae-seok Yang, Principal Geotechnical Engineer from MIDAS IT headquarters. Today's session is on the deep excavations and dewatering in urban environment. This is an overview for the today's session. First, I will briefly walk through the modeling of excavations. Then I will overview the prediction of ground movements. And then I will present about the 3D excavation modeling. And lastly, I will introduce the case study. The surcharge loading to be used should be compatible with the particular situation being modeled. However, in most cases, a surcharge loading to model construction traffic, storage of material adjusted to a retaining wall, and so on, should be included. British Standard Institution, for example, recommends that a surcharge of 10 kilonewtons per square meter should be included to model such effects. The pressure of compacted field on retaining walls may be a significant factor in the imposed loading. Clayton and Simmons outlined an approach for calculating these pressures. This is no doubt that the building stiffness alters the pattern of a retaining wall and the ground movement over the greenfield situation. In any soil structure interaction situation, relative movement of the structure with respect to the soil can occur. The use of continuum elements with compatibility of displacement in a finite element analysis of this situation prohibits relative movement at the soil structure interface. Nodal compatibility of the finite element method constrains the adjusted structure and soil element to move together. Interface elements can be used to model the soil structure boundaries such as the size of a wall or a pile or the underside of a footing. Particular advantages are the ability to vary the constitutive behavior of the soil structure interface, that is the maximum wall friction angle, and to allow differential movement of the soil and the structure, that is slip and separation. The interface material can be defined using the following equation. Using the stiffness of adjacent element and nonlinear parameters, the virtual thickness and strength reduction factor is applied. Interface material stiffness and parameters are applied differently according to the relative stiffness difference between neighboring ground and structural members. The wizard can be used to simplify this process. The general strength reduction factor for structural members and neighboring ground properties are as follows. Checking the element size considerations calculates the interface material properties considering the average length, line, average area, pace of the neighboring ground element when creating an interface. In other words, the average length, average area are multiplied to the virtual thickness in the equation below to calculate the tangent normal direction stiffness of the interface. A variety of techniques is used to model props and anchors. When the prop is external to the structure, it may be convenient to model the prop as a linear elastic spring with spring stiffness being specified in the relevant directions. Full moment connections, such as that due to a reinforced concrete slab acting as a prop, can be modeled using solid 2D elements. The load distribution can be obtained from the compressive stress at the integration points. Anchors can be modeled by bar elements, and it is relatively easy for the program to calculate the excess force over the initial value. Beam elements have rotational as well as displacement degree of freedom and therefore are capable of transmitting moments as well as axial force. Now I will overview the prediction of ground movements. It is now well recognized that in order to satisfactorily predict wall and ground movements resulting from deep basement excavations, a constitutive model which assumes linear elasticity should not be used. Jen states that a review of published analysis strongly suggests that the lateral wall movements are not very sensitive to the type of constitutive law adopted, at least as far as excavations in steep soil are concerned. The situation is different regarding vertical ground movement. Borland and Hancock illustrate this finding, for example, in their classic paper on the deep excavation at New Palace Yard in London. They assumed a linear elastic constitutive model and were able to predict the maximum measured movement relatively accurately. However, the pattern of movements predicted was inaccurate. This includes a prediction that the Big Ben clock tower would tilt in a direction exactly opposite to that which occurred. Also, the linear elastic model tended to overpredict the movement of the toe of the retaining wall. Thus, a constitutive model which incorporates nonlinear elasticity, particularly at small strain, should be used in this circumstance. When choosing a constitutive model, the following aspects need to be considered: soil nonlinearity, actual result strains in the ground due to excavation, and technique for deformation of ground stiffness. It is well accepted that soil stiffness is nonlinear and that the stiffness degrades rapidly with strain. The concept of the S-shaped curve, uh, figure in the slide, to describe this phenomenon has been well documented in the literature. Relevance of small strain stiffness are very stiff behavior at very small strains vibrations, reduction of stiffness with increasing strain, restart after load reversal, high hysteresis in cycling loading, energy dissipation or damping. Also relevant for applications like excavations, settlement through behind the retaining wall, or tunnels, settlement through above tunnel. It must be recognized that the strains in the ground resulting from deep excavation are very small. Figure shows that the predicted shear strength resulting from a wall displacement of 0.2% its height vary between 0.01% and 0.1%. The figure of 0.2% height is relatively high, thus real strains are likely to be even smaller than this. The stiffness values used in any analysis must be the appropriate values for the likely strains. The S-shaped curve shows that for strains in the typical range encountered in retaining walls, conventional triaxial test results are not applicable. This is because of bedding type errors associated with measuring displacement in conventional triaxial shells. Special triaxial equipment with local transducers mounted on the specimens is necessary. If stiffness values at strains lower than about 0.001% strain are required, then data from equipment such as the resonant column or vendor elements are needed. As the mechanical behavior of soils depends on the current effective stress state and stress history, it may be important to obtain soil stiffness estimates from tests which follow a stress path compatible with that experienced by the soil at the particular site. And discuss this problem, and his approach is shown in this figure. There are many constitutive models available in commercial finite element packages for carrying out analysis involving nonlinear or small strain stiffness. More common is unrealistic deformations. Use of single stiffness fails to cater for the complex material at various zones, and overestimation over bottom heap, and sometimes heap of soil behind the wall, and soils below excavation behaves with unloading stiffness. Even soils behind walls behave between unloading stiffness and the secant stiffness. Use of secant stiffness is too conservative. Hardening soil model is qualitative realistic deformation. Soil stiffness for isotropic loading, shearing, and unloading reloading can be catered for automatically in the model. More realistic bottom heap, and improve settlement through behind the wall. Hardening soil with small strain stiffness model is qualitative and quantitative realistic deformations. It is improved over hardening soil, general hardening soil, to take care of far-field small strain behavior, and actually it is more realistic settlement through behind the wall, narrower or deeper. Possibilities and advantages compared to Mokulon model are better nonlinear formulation of soil behavior in general, both soft soils and hardest type of soils. Distinction between primary loading and unloading reloading. Memory of pre-consolidation stress, and different stiffness for different stress passes based on standard test. And well suited for unloading situations with simultaneous deviatory loading, for example, excavations. And lastly, large stiffness at small strain levels, such as vibrations, but this effect is only with hardening soil with small strain only. The consideration of an isotropic yield surface has significant consequence in the case of excavation in soft to medium soils. As the figure shows, on the passive side, the main yielding of the soil occurs much earlier if a more realistic anisotropic bounding surface is adopted. Loading due to groundwater is clearly a very important component of the force acting on a retaining wall. Often, there will be a lack of relevant information in ground investigation reports. In order to overcome this, British standard, for example, suggests a conservative groundwater regime should be assumed for design purpose. A set change in the flow water pressure in part of finite element meshing may be required. For example, during excavation in layered soils, it may be necessary to dewater granular layers to prevent bottom heave. For every excavation stage, in case of undrained excavation, firstly, excavate soil and then set excavate area with the dry situation condition. And the protection level outside the excavation remains unchanged, therefore suitable for short-term excavations in low permeability soils. In case of drained excavation, similarly for every excavation stage, firstly excavate soil and define boundary condition using the head boundary and perform CPG analysis. Purity level outside the excavation lowers, so it's suitable for long-term excavation in high permeability soils. Yeah, actually, G-shape purity level gives wrong result. No equilibrium in horizontal water pressure. So local peak stress here is kind of discontinuity, and local peak strains and non-physical horizontal displacement and non-physical excess flow pressures. So possible incorrect water pressure acting on wall. So figure on the left hand side is the long way of modeling the water pressure, as I mentioned, since due to the discontinuity between excavation region and behind of the wall. So this can be overcome by interpolation of water pressure between two material zones in GTS and X. Now I will present about the 3D excavation modeling. Although there are many geotechnical problems that can be approximated to either plane strain or asymmetric conditions, some remain which are very three-dimensional. Such problems will therefore require full three-dimensional numerical analysis. In reality, most geotechnical problems are three-dimensional, and although in many plane strain or asymmetric approximations are not unreasonable, there are some which must be treated as three-dimensional. Most basement excavations are three-dimensional in nature and require some degree of idealization to two-dimensional plane strain to render them should within realistic turnaround time on existing computing platforms. We need to consider carefully what is the effect of such idealization on the solutions. One of the significant advantages when using 3D finite element method is the corner effect. In 2D FE model, the model is assumed as infinitely long. So, that is the plane strain. However, the length for width ratio has dramatic influence on the behavior of the retaining structure. When the pit is not long enough, the maximum displacement and bending moments would be much lower than 2D based calculation based on the arching of the wall. Wall length to depth ratio, low length to depth ratio. So it's a more significant core effect. If excavation is underlain by stiff soil, then maximum wall deflection is reached above excavation level, and corner effect may be superpressed if sufficiently steep strutting systems are used. If excavation is underlain by soft soil, maximum deflection often reaches below excavation level, and steep strutting system does not superpress corner effect. So this slide shows the conclusion on 3D modeling. In comparison with 2D numerical modeling, the most influential factors are the geometry and mesh setup. The engineering theories applied are the same in 2D and 3D modeling. The difference in resulting are most likely to be caused by the geometry of the investigating domain, namely the corner effect in 3D modeling. The rotation and deformation of corners could not be modeled in 2D models. And the advantage of applying 3D FEM modeling would be more significant when the construction and excavation domain is more complex. The case study provides a summary of a research project related to the analysis of contiguous file retaining walls using limit equivalent method as well as finite element method using MIDAS GTS NX. The selected geometry, construction, sequence, and soil conditions are based on 4-meter deep excavation required for the construction of a rainwater attenuation tank at Birmingham New Street Station redevelopment project in UK. The object of the study has been to investigate the analysis of retaining walls using limit equivalent approach as well as 2D and 3D FE models and compare the result with some field data to conclude on advantage and disadvantage of all three approaches. The study obviously has a wider application to a variety of civil engineering and infrastructure projects, such as construction of deep basement excavations, buried structure and services, and the effect of such excavations on the surrounding areas and adjacent structures. Initially, I will give a very brief introduction to the fundamentals of the theoretical analysis and objectives of the study. I will then give details of the research case study followed by methodology where I will go through the ground conditions and various analysis models. I will then go through the analysis result followed by the conclusions of the study. To allow detailed design, a thorough analysis is used to investigate design and construction options, optimize geometry, and to check that soil and structure are not overstressed. For full analysis, the behavior of soil, structure, and their interface should obviously be considered. Mathematically, a complete theoretical solution should satisfy the requirements of these four conditions for force and displacement, and equilibrium deals with over force and moments, and the compatibility is about physical and mathematical displacement and strains. And material constitutive behavior links stress and strains, and thus a link between equilibrium and the compatibility. Boundary conditions defines the nature of the problem boundaries. In terms of the method of analysis, fundamentally there are two groups, conventional method and numerical method, which I will briefly provide some description. Closed form provides an exact theoretical solution, but it is based on unrealistic assumption that soil is an isotropic linear elastic material. Simple method involving realizing one or more of the solution requirements, usually the compatibility. These methods are subdivided to limit equilibrium, stress field, and limit analysis. All simple methods assume the soil at failure and assume soil behave either undrained or drained. They provide information on stability only, and they fail to satisfy all of the four theoretical requirements in the left-hand side. In beam spring approach, the soil behavior is approximated by a set of either unconnected vertical and horizontal springs or linear elastic interaction factors and only one single structure can be modeled at any one time. Full numerical analysis, however, satisfies all theoretical requirements, including realistic soil constitutive models, and incorporate boundary conditions to reflect field conditions. The, accuracy of the method is depending on the ability of the constitutive model to represent the soil behavior and correctness of the boundary conditions imposed. Until recent years, the analysis of retaining structure have been done by simplified methods such as Rankine and Coulomb method or traditional limited equilibrium method, which are based on conditions at collapse when the full strength of the soil is mobilized. Limited equilibrium calculations do not in themselves give any indication of wall movement, although some computer software consider the interaction between the wall and the soil to provide some suggestion of wall deflection. Most of these methods simplify the 3D problem to a 2D problem. Fundamentally, limit equilibrium design method for the analysis of embedded retaining structure assumes the wall to be rigid and the soil to have a rigid, perfectly plastic behavior. The earth pressure deriving from the interaction depending on the expected movements of the wall and the mobilization of active and passive lateral earth pressure triggered by such movement. Technically, full numerical analysis is the only method that satisfies all the theoretical requirements discussed earlier. It allows for realistic soil constitutive models, incorporate actual boundary conditions, represent the soil behavior with the correct geometry, allows for modeling the initial stress state, construction process and soil structure interaction, consolidation analysis, and so on. The research case study relates to the 4-meter deep excavation works required for the construction of an attenuation tank at Birmingham New Street Station redevelopment project. The attenuation tank was to be formed using contiguous CFA filed walls and with base and roof slabs, which you don't see here but will be shown later. The slabs act as truss in permanent conditions. However, in temporary conditions, that is during excavation to form the tank, the wall acts as a cantilever for which any excessive deflection would have affected the structural steelwork already installed and supported by a number of contiguous piles. The photo on the left shows the steelwork which had to be installed prior to any excavation. The ones on the right are obviously the 3D models of the steelworks and attenuation tank below. The three columns supported by the contiguous piles were at offset from the piles and thus inducing a moment to top of piles. In permanent conditions, this would have been resisted by the tank's roof slab. However, in temporary conditions, this exceeded the file capacities and would result in excessive deflection of the piles. We assessed the piles for temporary and permanent conditions, designed the steel tools for already fabricated columns and file caps to spread the load and utilize the increased stiffness of the wall. Due to construction program and importance of installation of facade works on time, The sequence was to install CFA files, then the steelwork and deck to be constructed to provide the required access and platform for mobile cranes, spider crane, and then the attenuation tank to be built underneath whilst the other construction activities progressed on the steelwork deck. The picture on the left shows the installation of the facade steel frames with mobile crane on the deck, while the photo on the right shows an ex excavator digging for the new tank. You can also see the yellow boom of a mobile crane on the deck. This slide shows the simplified details of the problem I used for the modeling. The left-hand side is a simplified extract from the structural drawings indicating the 600 diameter contiguous piles at 750 centers and the 3 steel columns and 5 caps to one side of the tank only. The right-hand side is a section through the tank. The structure of the tank also requires some bearing and reinforced concrete ground beams to support the tank in permanent conditions and when at use. Here is the construction sequence and imposed loadings. Analyses are carried out to compare the main factors of wall bending moment, wall deflections, proof force, or in our case slab force, time spent on modeling and analysis. As I mentioned earlier, there are also some field data available from surveying the top of contiguous piles for lateral deflections during excavation, which are compared to the theoretical results. Ground investigation report confirmed the existing ground in the vicinity of the attenuation tank is uh, consists of 3 or 4 meter of made ground fill on a thin layer of sandy gravel on medium dense and undrained by extremely weathered sandstone formation. No groundwater was observed on any of the 6 borehole logs, and therefore the water table is assumed to be well below the excavation level. The values of phi are estimated from the SPT N values and soil descriptions of borehole log. For normally consolidated sand, the earth pressure coefficient and rest is calculated using equation shown here. The lateral active and passive earth pressure for limit equivalent method are worked out as suggested by British standard. Reviewing the soil parameters closely indicating that the critical values of sandy gravel and sand layer are fairly similar. Considering that sandy gravel layer is estimated to be only 1 meter thick and the majority of it will be removed from on the excavation side, the effect of substituting this layer with increased thickness of sand layer for the ease of analysis is investigated. Most engineers in practice would probably take the same approach. As the soil friction angles and soil stiffness modulus are approximations, an initial sensitivity exercise is carried out to study their effectiveness at a variation of plus minus 5%. For the limit equilibrium method, the computer program used consists of a series of linked software modules capable of analysis and design of embedded retaining walls. It is widely used by civil engineering contractors and file designers to analyze construction sequence and excavations to design embedded and proofed retaining structures, including contiguous board files similar to our case study. The file geometry and the soil profile of the case study are inserted to the program, followed by setting up the construction sequence as discussed before. In addition, various other soil and design parameters are also input to the program, including prop, Weyler stiffness modulus, prop spacing and length, analysis options, and so on. In temporary conditions, the wall acts as cantilevered, while in permanent conditions, base and roof slabs act as struts, and the ice barrier wall can also apply 65 kN per meter horizontal load to the file head. The analysis results are then automatically tabulated for each construction stage in terms of the wall's shear force, bending moment, and deflection, as well as the factor of safety at given depths of the wall. The structural details of the files can also be determined in terms of main and shear reinforcements. In either cases, as you can see, the limit equivalent method only considers half section of the problem, which is a function of the method. The main objective of studying retaining wall stability through finite element method is to calculate displacement, stress consistent with ground elastoplastic characteristics, and the interaction between retaining wall and structural members. MIDAS GTS NX is a fully integrated 2D 3D FA software used to evaluate the application and effectiveness of finite element method for the analysis of the case study. For all ground material, an isotroping Mokulon constitutive model is used as it is defined by an elastoplastic behavior and provides reasonable result for general nonlinear analysis of the ground. For structural materials, that is contiguous piles and icy slabs, the isotropic elastic model is used. Identical soil and the structural parameters are used as per limit equivalent method. In 2D FEM, soils are modeled as 2D plane strain elements along with 1D beam elements for files and slabs with their section property set. Slabs are modeled as 1 meter wide strut in 2D environment. In 3D FEM, all soil models are modeled as 3D solid. Base and roof slab are treated as 2D plane stress elements and contiguous piles as 1D beam elements. As the wall is fairly thick, it could have been modeled with 2D plane stress elements with equivalent section properties. The moment of inertia of 600 meter diameter contiguous piles at 750 millimeter centers is approximately equivalent to a 430 millimeter thick wall. However, to be consistent with 2D model, this option is not pursued. The initial remark between 3 layers and 4 layers soil analysis is indicated by LEM analysis on the stability safety factor, which decreased from 3.19 to 2.76 when the sandy gravel layer with the friction angle is the 35 degree is substituted with sand layer with the 34 degree. The wall bending moments shows less proportionality, especially for 2D and 3D FE models, which predict the maximum wall bending moments to be approximately 30% lower than limit equivalent method suggestions. The 3D model correctly suggests the worst case scenario occurs at middle columns. Thus, the graphs for 3D method are based on this specific location. These graphs indicate predicted deflections for all 3 methods follow a similar pattern and reduce uniformly by 1 or 2 millimeter maximum at the top of the wall from 4-layer soils to 3 layers. To keep things simple, the sensitivity of the key analysis outputs with respect to plus minus 5% variation on soil stiffness modulus and friction angles are present for three layer soil at excavation stage. This is the sensitive result of sensitive study from limit equivalent method, considering 5 cases. All 3 methods suggest the stiffness modulus 5% variation has very little effect on walls deflections and bending moments comparing to friction angles, which has a drastic inverse effect as illustrated by graphs. This case shows the 3D FEM result for 5 cases. Maximum bending moments were in the range of 150 to 60 for limit equivalent. In case of 2D FEM, 88 to 108, and in case of 3D FEM, suggest from 89 to 106 kilonewton per meter. The limit equivalent safety factor on stability also showed significant variation of plus minus 20% when friction angle varied at 5% in this case. So stiffness modulus on its own had negligible effects on the stability of the cantilevered wall. Considering the cantilevered wall already supporting the earth and column rows, that is passive resistance mobilized, once the slabs are connected, we wouldn't expect much of a load before barrier wall is applied, unless if relaxations or age analysis is modeled, which is not the case here. However, as the connections are modeled as pinned in all 3 methods, this results in base slab in tension and the top slab in huge compression. In reality, however, this is not the case, as the base slab can only resist compression. By deactivating the base slab, we get more reasonable prop loads. The limit equilibrium model did not consider the initial mobilized passive resistance at all and suggests a huge base slab load, but with the loop slab in, it suggests a more realistic number, but still based on an incorrect approach, therefore a problematic function of the method. This situation is due to the deformation shape of the walls and slabs as one structure when subject to line and moment loss at the file has in an asymmetric profile. Limit equivalent model assumes a symmetrical behavior and ignores the 2D geometry of the structure along with the associated load path. And suggested limit equilibrium result look less drastic, though they have not been calculated incorrectly. It is most worth to note that analysis of half section in 2D finite element analysis would not have predicted this asymmetric behavior either. This figure on the right illustrates the displacement shape in 3-dimensional and the location with relatively higher displacement due to moment load applied by the columns. Limit equivalent method is not capable of modeling this at all. This slide is perhaps the most critical slide of this webinar, as the graph indicates the summary of research in temporal conditions, which is the most critical. In short, both finite element models suggest lower bending moments with more realistic shapes. It is obvious that the maximum bending moments suggested by limit equivalent method are more than 50% higher than both 2D and 3D finite element models, which suggest fairly equal values and a more realistic profile. Limit equivalent method indicates zero bending moment in the wall where passive and active moments are equal. that is safety factor of 1. In terms of deflection, the 3D model illustrates approximately 40% lower values than 2D FEM model and the LEM model. All 8 pile heads supporting steel columns were monitored during excavation, as I mentioned, using total strain EDMs for possible movements. Displacement recorded on daily basis during the excavation works were very minimal, and in the other of 3 or 4 millimeter towards the excavation side. It can be argued that the live loads from columns or the surcharge on the active side are for design purpose and can vary significantly in practice. By removing the surcharge and the moment load, the maximum fire deflections reduced to 6 millimeter in 3D model, which is even closer to what was observed on site 4 millimeter. Ignoring the instrument tolerance, which is a big assumption due to small deflection, this reinforces the statement that design live loads are not reliable to compare the result of theoretical analysis to field data, unless if the design values are controlled and verified. Nevertheless, the finite element 3D model results are closer to the field data available. As far as the research is focused on with regard to limit equilibrium and FEM, both methods are pretty much based on similar theoretical assumptions and certainly initial soil parameters, which makes the study still valid. Similarly, in permanent conditions, where the roof slab is in compression and acts as a support, the FEM proof loads are less than limit equilibrium by 25%. Ability to operate the programs has been the main part of the research project. In the case of MIDAS GTS NX, online operator manuals and a number of tutorial clips published by MIDAS have been used to learn the modeling and analysis functions. The layout is user-friendly considering the complexity of finite element modeling, and the quality of produced results are impressive. The 2D modeling takes significantly less time comparing to the 3D modeling. 3D modeling can be challenging until the functions and methods are learned in depth. The modeling time clearly depends on the complexity of the problem. During this project, the 3D modeling and analysis took approximately 6 times longer than 2D modeling, including exploring various modeling options. Obviously, the 3D model provides the more realistic result than the other method. In the case of LEM, limit equilibrium method, the learning process is much more simplified, and assuming all soil parameters are available, one set of analysis can be done in 2 or 3 hours. These conclusions are made based on the analysis performed. All methods suggest the stiffness modulus 5% variation on its own has very little effect on walls deflections and bending moments comparing to friction angle, which has a drastic inverse effect. This was particularly noticeable for the 2D FEA model, where 2 degrees decrease in friction angle increased the pile head deflection by 50%. I should mention that bigger variation of elastic modulus should be considered in case of uncertainties in the initial stiffness values. Due to asymmetric profile of the problem, full section 2D and 3D FE model predict more realistic deformation shapes, although the prop connections had significant effect on behavior of the structure. Limit equilibrium missed this criterion completely, whilst analysis of half section in finite element would not have predicted the asymmetrical behavior either. Maximum bending moments were in the region of 150 kN per meter per limit equilibrium, while both FE models suggest 90 to 110, which is the 30 or 40% reduction. 2D and 3D FE model props loads were approximately 24% lower than limit equivalent suggestions. Maximum pile deflections illustrated by the 3G FE model were closer to available site observations and approximately 40% lower than 2D FE model as well as the CAS PWS result. In general, although 3D FEM model and analysis time were significantly higher, this method provides the most realistic soil behavior with least amount of wall deflections and structural forces. Future research should consider the effect of other soil constitutive models such as hardening soil model, sensitivity to messy and interface element types, as well as proof concrete relaxations and preloading.